Okay, good morning. Welcome to
FamilyMath1151.
FamilyMath1151. So yesterday we proved that you can take the positive integers and make a one-to-one map to the rational numbers. So like 3/4, 10/7, etc.
Yep.
And what that showed is that the rational numbers have the same infinity as the real numbers, or sorry, the positive integers.
The same size infinity.
The same size infinity, which is pretty surprising. The thing though is we didn't actually quite create a one-to-one map. So we did something slightly different, and I wanted to just make sure you understood exactly what we did there, because it's actually kind of important, and then we're going to take a look at why the real numbers can't be put into a one-to-one correspondence.
Okay.
All right, so you came up with a very clever argument that I'm going to stick with, that just goes from 0 to 1.
Okay.
And you said, what I'm going to do is I'm going to take the points, I'm going to represent rational numbers by an ordered pair, which is a great thing to do.
Yep.
And like this one, for example, the x coordinate's 1, the y coordinate's 2, and you said, so this is going to be the rational number 1/2.
That represents a half.
And then this one was 1/3, and this was 2/3, 1/4, 2/4, 3/4.
Yep.
1/5, 2/5, 3/5, 4/5, and then you just walked up this path.
Yep.
Okay. And that was where we left off yesterday. And we basically said we're done. But actually, this is not a one-to-one map to the rational numbers. So why not?
Well, I mean, this only covers from 0 to 1.
Oh, yeah, sorry. This is not a one-to-one map to the rational numbers in 0 to 1. Yeah. As long as we get 0 to 1, we're done. We did that yesterday. But this actually doesn't do that. It doesn't create a one-to-one map from the integers to the numbers, the rational numbers in 0 to 1. So something actually didn't work correctly here. But it's not a problem. It just isn't quite, when we say this is a one-to-one map to the rational numbers in 0 to 1, that's not actually right. Do you see the problem?
Well, I mean, we didn't really approach it in the same way as we approached some of the other ones, like the positive integers to the even positive integers. There we created sort of a formula.
Yep.
But here we sort of just created like a map that you can walk along.
Yeah, that's all right. We could actually write down the formula for this map, believe it or not. So we don't necessarily need a formula, just a little map. I'll give you a little hint by writing out the numbers to help you see what the problem is. Sorry, I'm writing. Am I staying on screen here?
Yep, you are.
And etc. These proceed like that, but there's a problem. Even with the numbers I've written down here, there's a problem.
Was it the duplicates? We have duplicates.
Yep, we have duplicates. 1/2 and 2/4. So in fact, this set. What can you say about this set of numbers compared to the rational numbers?
It's, well, I mean, if you wrote them down like this, it's going to be larger because you have duplicates.
Yeah, it's larger than the rational numbers. So we actually created a one-to-one map that actually has these duplicates. In fact, how many times is each fraction going to be duplicated?
Infinitely many times.
Infinitely many times. So not just duplicates, and not just a little bit larger. This set's actually a lot larger.
Yep.
So why isn't that a problem?
Well, both sets are sort of infinitely large. I suppose you could have different sizes of infinities. Maybe.
Yeah. It's tricky. So let's go to the second video and I'll explain why this is okay. Because it's an interesting argument that you have working with sets. Okay?
All right.